So I'd now like to just summarize the main scientific ideas of the week and to conclude by telling you and indeed proposing what our equation of the week will be this week. So we've talked about viscosity. We've talked about viscosity in simple fluids and we've talked about viscosity in complex fluids. The main idea for both cases is essentially the same. Namely, for example, in a simple fluid we have lots of little particles. These little dots are supposed to be molecules, and the molecules move around, and it's the motion of the molecules by each other that leads to the viscous motion of the fluid. If the fact that the molecules have to move around each other in order for the whole thing to flow basically leads to a resistance to flow, and that's what we mean by viscosity. So that's the story in a simple fluid. Now in a complex fluid, the answer is the same thing. Namely, there's some background state, which is the simple fluid. Namely, these little molecules that I drew for the simple fluid are still there. But now, in addition, we also put in big blobs. And so let me draw some blobs. These are blobs, and these blobs can also move around, and actually the fact that these blobs now have to get by each other in order for the fluid to be able to flow means that the complex fluid is going to have a higher viscosity than the simple fluid. Now, Dave and Nathan Myhrvold, in their discussions, basically told you about a number of different kinds of blobs. So one kind of blob, which I'll just draw here, is just a solid particle. So this is a solid particle, and as such, you have to get out of the way if you want to go by it. That's one sort of blob. So another sort of blob is a starch granule, and actually let me draw that from scratch. So a starch granule might start out being little, but then when it's put in water or some fluid, it will get bigger, and then it will become a bigger blob. So the little starch granule becomes a bigger particle, and it's harder to get around. And the third type of element that we put into our blobs were polymers. And let me just draw this in here. And the point of a polymer is that it actually takes up very little weight, but it actually fills the blob with a random walk, and so so you have to get around the whole blob in order to move. And so a complex fluid in general can have all of these different things. It can have particle blobs, polymer blobs, whatever. And those blobs, basically, the fact that they have to move around each other is what gives the fluid a higher viscosity. Okay, so now with that as background, let me tell you about our equation of the week this week, namely the equation that we think best summarizes these ideas. So the viscosity, remember, we called eta. And let me call eta naught, eta with the subscript 0, that's the viscosity of a simple fluid. So this is like the viscosity of water. So this is going to be the viscosity of a simple fluid, and it's some low number because, simple fluids, at least unless they're in an unusual state, tend to have a low viscosity. What we're really interested, of course, is the viscosity of a complex fluid. And the viscosity of a complex fluid basically is the viscosity of a simple fluid times some function of the volume fraction of the stuff, of the junk that you put in the fluid. So phi, I'm going to call that the volume fraction. So that's the volume fraction of the junk, of all the stuff you put in. Are they starch granules, or are they polymer blobs, or whatever they are? And the main point of this, actually, is that if you were going to actually plot the viscosity, so if you were going to plot eta as a function of the volume fraction, then it would start out at some low number, and it would then rise very, very rapidly. And actually, it even becomes infinitely large once phi is at a number that's sort of close to around 0.6 or so, which is where basically the volume fraction is so large that the blobs that you put in just get stuck. So for our equation of the week this week, instead of actually making it boring and making it the equation for the viscosity, what I guess I'd like the equation for the week to be this week is just the definition of the volume fraction. The volume fraction is the volume of the stuff that you've put in, so volume of stuff, divided by the volume of the fluid. It's just the fraction of the fluid that is filled with stuff. And this is really the important thing, because basically when you're trying to thicken a sauce, what you're trying to do is increase this volume fraction. And you have to be a little careful when you do it. As Dave described to you, when you, for example, consider a polymer blob, the relevant volume is the volume of the polymer blob that it spans out, including the water that it contains. So since a polymer blob is a random walk, we don't mean just the volume of the brown ink here. What we mean here is the volume of the whole brown ink plus water that it has within it. And this idea of volume fraction, really captures the idea of this weak, because it basically is the major determinant of the viscosity. And when you're trying to thicken something, that is really the quantity that you're trying to control. You'll remember, and you saw this from Nathan Myhrvold and also from the demonstrations of Carles Tejedor, which you will see in a minute, that if the volume fraction gets too large, or if these blobs happen to be too sticky, then the material can easily stop flowing, everything gets stuck, and then it becomes purely elastic. So there's a very, very short borderline between something being viscous and being able to flow very slowly, and something being elastic where the blobs are just stuck to each other and it can't flow.